Hello, this is Nongtao Yuan. Thank you for joining this year's Lattice Development Conference. In this session, I am going to give you some introductions about how we leverage Lattice Sense AI Stack to develop an AI solution for the real-world application. I am from the System Solution team in Lattice Shanghai. My focus area is to work with different APAC customers to develop AI-based solutions with Lattice FPGA. I have been working in signal processing and the AI algorithm development field for over 17 years. Here is the agenda for this session. Firstly, I would like to give you some brief overview about the Lattice Sense AI stack. Then in the second section, I would like to share you our workflow of using Lattice Sense AI for the real-world projects. In the third section, by taking the color sort AI design as an example, I will showcase how the workflow was executed step by step. There will be a quick summary in the end. After that, we can discuss about some frequently asked questions. This page is the overview of Lattice Sense AI stack. It illustrates what Lattice Sense AI can provide to the users. Generally speaking, Sense AI stack enables users to deploy AI model inference on Lattice FPGA in a very efficient manner. One important thing is that users do not need to develop the NN accelerators by themselves. Instead, they just need to focus on the AI model training and the overall algorithm pipeline design. It is able to support different Lattice FPGA platforms, different CNN model architectures, and different training frameworks. Users can also find more details about Lattice Sense AI from the website. Based on our practice for the real-world AI design, we summarized the basic workflow of designing with Lattice Sense AI toolchains. At the first step, after a new AI requirement is connected, we need to do some feasibility analysis first. At this stage, we analyze system requirements and then propose a customized AI algorithm pipeline. A CNN model will be part of this AI pipeline. Particularly, customers usually have some definitions about the algorithm accuracy from the system level requirements. Therefore, in this feasibility analysis, we need to do some early assessment for the AI model accuracy and answer one key question. Can we meet the accuracy requirements with existing AI techniques which are supported by Lattice Sense AI? If the answer is yes, then we will go with some other feasibility evaluations, such as the interfaces, the power consumption, and so on. After the feasibility analysis is done, we will review it with system engineers and then get their confirmations. The second major stage is the AI model development with Sense AI stack. At this stage, for the training data, we need to take more data labeling and augmentation work. For the AI model part, we need to select and train a Sense AI compatible model. For the FPGA part, we need to determine which NN engine should be selected. After that, we can evaluate the model performances more accurately. It is noted that at this stage, the model performance evaluation is taken in software environment. The third major stage is to implement the complete AI algorithm pipeline in RTL. Besides inserting the NN accelerator, we also need to design some other modules such as the non-AI algorithm module, the image pre-processing module, and the model post-processing module. The next major stage is the system integration. We need to integrate our AI algorithm pipeline into the real system and then do the system level validations. The overall system performance will be also tested. At this stage, the AI model will keep being updated if we found some unsatisfactory performances for some corner cases. In the following section, I am going to showcase some details about our design practice in the AI-based color sorter solution. This requirement comes from a customer who is in the color sorter machine industry. You can find the basic diagram of a typical color sorter system in this figure. The materials to be sorted will be falling down from the top to the bottom one by one. A line scan CCD sensor is usually used to capture the image of the fast-moving materials. A net source will be positioned at the background. Then, a processor will be used to analyze the line scan image stream and identify the defective materials. If one material piece is identified as a defective one, some ejector will blow away this piece. Otherwise, this material piece will keep falling down and be connected as the good products. This kind of sorter machine is called color sorter because the previous generations of color sorters identify the defects mainly by checking the material colors. The problem is that for materials with very complicated colors and shapes, only checking the color cannot provide a satisfactory accuracy. We defined the system requirements together with the customer and listed them in the table. In this specific color sorter machine, the Sichuan paper is the material to be sorted. The system has a line scan sensor with 10,000 lines per second. For each paper patch, we need to finish the detection and output the result within 5 milliseconds. The accuracy requirement is 98% for precision and 96% for recall. At the feasibility analysis stage, we need to clarify some key requirement features. For the AI algorithm part, we highlighted 3 key features. Firstly, as we need to output the results of both piece locations and piece types, this AI task should belong to an object detection tab. Secondly, there are clearly defined performance requirements, including both the model accuracy and the inference time. Last but not the least, we identified 2 uniqueness of this AI requirement compared to some other typical object detections. Number 1, the object to be detected has a very small size. As a result, we need to provide a high resolution input for the AI model. Number 2, the processing latency should be very small. So, a traditional frame-based AI processing pipeline can hardly meet the latency requirement. Furthermore, some other essential requirements from the system are also considered and listed here. Those requirements affected the design of the peripherals. According to the system requirements, we designed a customized AI pipeline as shown in this page. Basically, the overall pipeline includes 2 parts. One part mainly includes the patch segmentation function, which is used to extract the paper patches from the video stream. The other part is the CNN-based image classification function. Some additional pre- and post-processing modules are also included. With this customized AI pipeline for each image patch, we did not take any downsampling operation. Therefore, we preserved the original resolution for the AI model input. Furthermore, each patch will be processed immediately after it is captured by the image sensor. No frame buffer is used. As a result, the latency can be very small. What's more, for each patch, we just store the data of small ROIs with the large RAM inside FPGA. So we did not need any external volatile memories. With this patch-based processing scheme, we can fulfill the system requirements of high processing resolution, ultra-low latency, and low external memories. Then we came to the early accuracy assessment phase. This assessment work was conducted in a very agile way in order to give a quick but reliable algorithm accuracy assessment. In this phase, we formulated the classification problem into a 4-class image classification task. You can see that those 4 classes have explicit differences in the shapes. Then we prepared a small dataset quickly for the early assessment purpose. With this small dataset, we quickly built an AI model prototype. It is noted that this prototype model is not a quantized model, and it cannot directly run with Lattice FPGA. The reason why we designed this constraint-free model is that we wanted to evaluate the complexity of the problem itself. In this project, we chose a traditional ResNet-based signal model for this early accuracy assessment, and we achieved a precision of 95% and a recall of 95%. This accuracy was somehow below the customer requirements. However, after some further analysis, we identified that this accuracy loss was mainly resulted from the limited size of the small dataset. With this early assessment, we got the conclusion that with the small dataset and with a traditional signal model, we can easily get close to the accuracy requirements. The model performance could be further improved by both model and data enhancement in following steps. By now, we can summarize the feasibility analysis results as shown in this table. For both system interfaces and algorithm performances, we can meet the system requirements. Besides providing an ultra-low latency, this solution is also easy to be ported into the existing color sorter systems. The solution is also efficient in both the power consumption and the system BOM cost. After the feasibility analysis is done, we started the work of AI-based model development with the SenseAI toolchain. There are 2 major steps for this work. The first step is to design some effective data augmentation methods after analyzing the specific data pattern. Then, we introduced some customized data augmentation methods such as the rotation, resize, crop, flip, and so on. The second step is to design a SenseAI compatible baseline model. We started from the Lattice hand gesture detection reference. It is available from the Lattice website. Then we tuned the hyperparameters according to the system requirements. Those parameters include the input image size, CNN architecture, model depth, channel numbers, and so on. And at the training phase, we also adjusted the training scheme to carefully tackle the imbalanced class size issue. When an optimized performance is achieved, we froze the model architecture, and then the continuous performance optimizations were based on this baseline model. It is noticed that in this color sort design practice, we were training the model within the Keras environment. After the baseline AI model was built, we selected the engine type which is the most suitable to run this model with FPGA. For Lattice Cirrus Pro FPGA, there are different engine types that can be supported, which include the advanced CNN accelerator and the CNN Plus accelerator. In our color sorter AI solution design, we prepared engines with different configuration parameters by running the same model on them. Some of the comparison results are also shown as in this table. As you can see, the resource utilization and the model inference time are the main factors to be considered. In this example, the optimized CNN engine with dual conv and dual large ramps can achieve the best balance between the inference speed and the resource utilizations. As a result, this optimization CNN engine will be selected in our design. Then we came to the stage of the AI pipeline implementation in RTL. For AI model inference, we needed to instantiate the CNN accelerator in Lattice Radiant environment. One thing is to be emphasized is that we needed to make sure the configurations in Radiant should coincide with those settings in Sense AI Compiler. For other RTL parts, besides the NN accelerator, we needed to design some additional pre- and post-processing modules. In this color sorter example, we implemented the color space conversion module, dynamic padding and resizing module, and the optimized softmax module into RTL. Some of them are from the existing Lattice IP. Those modules work together to form a complete AI processing. Then we started to integrate all RTL modules into our Cirrus Pro FPGA. The system diagram is presented as in this page. The overall AI processing pipeline is constituted by the long AI processing module and the AI inference module. This AI pipeline is to be integrated into the final color sorter system. However, in order to conveniently evaluate the overall performance of this AI pipeline with an evaluation board, we also integrated some additional interfaces such as the HDMI receiver and the DP transmitter. Those interfaces helped us to do the image data injection and the result output validation efficiently. As a result, we can easily check the AI solution results on hardware with repeatable and quantizable test cases. After the complete FPGA processing system has been built and validated, we started to work with the customer and integrate the AI subsystem into their overall color sorter machine. Some on-site debug was taken, and the overall system function was checked. With the feedback connected from the field tests, we continuously optimized our design for both model performances and RTL implementations. It took us some time to iteratively improve the system performances and stabilities. Finally, with Lattice Sense AI toolchain and the Lattice low-power status pro FPGA, we achieved a system performance which can satisfy all customer requirements. After finishing this real-world AI design practice, we summarized some tips about how to effectively use Lattice Sense AI toolchains. Firstly, we need to tune the model architecture to follow Sense AI user guide. This user guide will help users to understand the toolchain, and users should be able to find the necessary information about how to use the tools. Secondly, users are strongly suggested to fully leverage Lattice reference models. It will significantly save the development time if users could build the model backbone with the suggested CNN blocks and design the model heads similar to the reference models. All those reference models can be found from the Sense AI model zoo. By now, I have presented all the stages that we have taken to design the AI solution for the real-world color sorter system. For this Sichuan paper use case, the Lattice status pro-based AI solution can effectively meet the system requirements. We can see that Lattice FPGA provides an efficient and low-power platform for such an edge AI application. Lattice AI toolchain also help users to quickly deploy the CNN models into Lattice FPGA. Before I wrap up, I would like to discuss about some frequently asked questions that Sense AI users may have. The first question: what are the major differences between design methodologies of Lattice Sense AI and other edge platform toolchains? Well, from my perspective, for the AI part, Lattice Sense AI almost has the same design methodology as some other edge platforms. Users optimize their model performances in popular frameworks such as Keras and TensorFlow, and then leverage Sense AI toolchain to deploy the model inference with Lattice FPGA. They do not need to care about the details of the model inference on hardware. Similar to other edge platforms, Lattice Sense AI toolchain also has some specific constraints for the model architecture. Users can easily find those constraints from the user guide. Some examples can be also found from the public reference designs. For the non-AI parts, such as the pre- and post-processing, I think Lattice FPGA usually run those functions in RTL. The implementations might be somehow different from the software-based platforms. Okay, the second question: how can we check the AI model inference result on hardware? I think several methods can be chosen. The first one is to build an AI simulation test bench and then run the inference in simulation environment. Then the engine outputs can be checked. The second operation is to run the hardware evaluation with Lattice evaluation board. The Sense AI toolchain provides a GUI to feed the stimulation data into some EVM boards, and then it can read back the model inference results from the hardware. Then we can start the evaluation. The third method is to build some customized platforms, such as what we have did for the color sort design, and the customer can build their own evaluation systems. The third question: what kind of image pre-processing and post-processing IPs are available now? For the pre-processing, some IPs such as video input and output interfaces, video scaler, debugger, color correction, and so on can be found from the Radiant tool. Some new IPs will be also released soon. For the post-processing, as it is usually application-specific, users can find some examples from the Sense AI reference designs. The first question: do we need an embedded processor to assist the AI processing? I think this depends on the AI task types and the system requirements. Generally, the computation-intensive CNN operations are taken by the Sense AI accelerators. But for some flexible post-processing steps such as NMS and clustering, an embedded processor may be a better choice. In this case, we can leverage Lattice Propel to build a RISC-V core for those processings. The RISC-V processor can be also used to do some task scheduling and system management work. If the system requires some high throughput post-processing, then the RTL-based modules should be more suitable. In this case, the RISC-V core can be not needed. Then the fifth question: where are the executive Lattice Sense AI binary stored? Can they be updated over the air? Okay. The generated Sense AI binary file is usually stored in the external flash memory. This flash memory can be also shared with the FPGA configuration flash. Users can enable the flash write operation in their design. In this case, they can do the model binary update over the air. The last question: how many FPGA resources are occupied by a Lattice Sense AI accelerator? I think the utilized resources depend on the different factors such as the accelerator type, the IP configurations, and the targeted device. It may be varying from around 1K LUTs to 100K LUTs. Please refer to more details from the CNN IP user guide.